Okay, so now we'll discuss the third problem. So this is the problem where we have a square and a disc, circular disc, and we want to cut each of them into two sets of pieces. The square is going to be cut into S1 and S2, and the circle is going to be cut into D1 and D2. And we want it to be so that S1 and D1 are homothetic, or in other words, if you scale S1, you can get D1, and same for S2 and D2. And the key is, we're going to have to use infinitely many pieces in these two sets. So here I have colored, Yannick and I have colored these two figures into a red set and a brown set. And you can see that the red sets, basically we do a circle inside the square, a square inside the circle, and another circle inside that, and a square inside a circle, and a square, a circle, and a square, etc. This will go for infinity. And then this one is just that same thing flipped. And the circles are on the outside, the squares are on the inside.
So you can almost think the circles are congruent right now.
Yeah.
Right?
You can, yeah, that's one way to think about it. And you just take the red one, you scale it down, and then you replace it here.
I see.
So it's the effect is just erasing the outer red part. So
what's the ratio of similarity for the red piece?
So that's the next thing you have to think about, right? The easiest way to do that would be to just look at the ratio of this side of the square to this side of the square, assuming we keep the round part fixed, right? So suppose the circle has radius 1. That means that this will be 2. And it also means that this length from here to here, this diameter, has length 2. So you have a circle,
Square inside.
yeah, square inside it, this is 2. It means the side is root 2.
So the ratio is scaling down of
It's scaling down by root 2.
factor.
Yeah. And then if we keep the red part fixed and scale the brown, it's the same as scaling up by root 2. This will be sad to erase.
Such a nice picture.